we're going to see the inductance of a conductor. Usually it is a solenoid, and we will see why Kirchhoff's loop rule is for the best, as Professor Lewin says. So I will do the same example that uses Professor Lewin. Let's say first that we have a simple circuit. Here we have the battery, let's say of 1 volt. Here we have a resistance R1 of 100 ohms. Here we have another resistance of 900 ohms. Alright. So now, what is the difference between this point, say D, and this point A? What is the potential difference or the voltage? Well, we can do it. It is very simple. First, we can calculate the current flowing, that it is by Ohm's law. We have voltage is equal to resistance times the current. So the current would be voltage divided by the total resistance, that is 1 volt over 10 to the 3 ohms, or 10 to the negative 3 amperes. So this is the current. Now for the voltage dropped, or the potential difference, we can take this way, or we can take this way, and we will see that it's exactly the same. So from this case, we have D minus VA is equal to 900 ohms times the current, that is 10 to the negative 3 amperes. So we have positive 0.9 volts of difference between D and point A. Now if we take this way, we have BD minus BA is, we have this battery. So if we move from here, we have first this drop in voltage, that would be 100 ohms times 10 to the negative 3 times 10 to the negative 3 amperes. This is the same drop, or what kind of similar to this drop, but we have here a plus in the voltage. So this is a negative, this is a 1 volt. So, and this is because the current goes in one direction, so for that the drop from this is, I call it a positive drop, and here we change the sign for this resistance, for that it is a negative here, and the battery is 1 volt. So again we have 0.9 volts. So we have again 0.9 volts in difference, and here it doesn't matter which way we take. But now, because we know that a change in magnetic flux can produce a current, so now our current supply will not be a battery. You can erase the battery. And now the power supply for this current would be a inductor. Let's say that the magnetic field is coming out, is pointing out of the board. So the current would be clockwise, because this is the, if here I'm pointing to this side, I see that the current will go in this counterclockwise direction, but the current that would be generating is opposed in the direction to which the current generate the magnetic field. So the current generated in this circuit would be in the direction, because this is the opposed direction of the current that generated the magnetic field in the first place. So remember that this inductor is usually a solenoid with a wire, so this wire is the current that is creating the magnetic field, and now this change in magnetic flux is producing this, well, the current going here. So now what is the difference from the 2A from this side, or measure from this side and measure from this side? We can see this if we attach a voltmeter here and another voltmeter here. Voltmeter. We could say that this is the positive end, the negative end, and here we could say this is the negative end, the positive end, or whatever it is. So again, we have in some moment the inductor would produce a voltage of 1 volt in some moment. So again, going in this direction, we have from VD to VA, or the potential difference would be just 900 ohms times the current, that is again 10 to the negative 3 amperes, because we are taking exactly at that specific part in which the self-inductor is creating a voltage of 1 volt. So here we have again 0.9 volts is the potential difference. Now if we go this way, and so this voltmeter will show 0.9. Going this way, we have VD minus VA would be equal to 100 ohms, well, negative, because I'm taking this, 100 ohms, and we have no battery, so it's just 100 ohms times 10 to the negative 3 amperes, and this is 0.1 volts. So in one voltmeter we see 0.1, and with other we see 0.9. So now this is a non-conservative field, because now the closed loop integral of E dot dl of the electric field is no longer 0. That this was Kirchhoff's loop rule. So now this equation does not hold. The equation that always holds is Faraday's law, that the induced EMF, the EMF is the electromotive force, that is actually voltage, and this voltage is the closed loop integral of E dot dl. This is equal to the negative time derivative of the magnetic flux. So this always holds. If we have a 0 change in magnetic flux with respect to time, then the closed loop integral of E dot dl is equal to 0, and we have Kirchhoff's rule. So Kirchhoff's rule is a particular example of Faraday's law, but it is very dangerous to think that this is a universal law, because this is one of the most counterintuitive concepts in electricity and magnetism. We will see quite more of the challenging in having this equation wrong, or thinking that this always holds when we deal with circuits that have inductor, because when we are trying to solve that equation, the differential equations, if we use this formula, we can get the same result, but it would be from a wrong equation, and we don't want that. We want to know the correct equation, the correct concept. So we know that Faraday's law always holds, and Kirchhoff's loop rule does not hold always. It is just a particular case. So this is what the inductor does. In the next video we will see it as the introduction to the AL-R circuits, and then we will do a CRL circuit. And now that we see this as Professor Lewin does is a super demonstration that many of them cannot believe. So this is the demonstration of why Kirchhoff's loop rule does not hold, and why we say that Kirchhoff's loop rule is for the birds.